So our next speakers are Sanjay and Dan, and I guess Jiannan's not, well, he's part of this, but he's not presenting. These guys are going to be talking about SampleClean. They're going to start with a demo and then give a talk. And I also want to note that Dan's favorite ice cream is pistachio, in case you guys were interested. Okay, so with that, this is a demo, so please help with your computer, and they'll explain all the details, but it should be fun.
Okay, go for it. Okay, so thank you all for taking time to come here. Today we're going to talk about SampleClean. I'm going to start off with a fun little demo to motivate data cleaning and why this is an important problem. And what? Yeah, and then Dan is going to talk about some of the research challenges. So let's get started. So this week is Big Game Week. I don't know if you guys all know. And as academics, we were really interested in how we could do our part. And the big question of our time is, who publishes more, Berkeley or Stanford? So what could we do about this? Well, we can go to Microsoft Academic Search and download a data set of academic publications to see if we can make this decision. And for those of you who are not familiar with this data set, it's a data set of papers, affiliations, and author IDs, and you can kind of aggregate all of these together. So we came up with a table of papers mapped to distinct affiliations, but the problem was it was still really hard to make this decision. Authors were really inconsistent with the way that they put their affiliation strings, such as Computer Science Division, University of California. Some people just said University of California. And there were other things that were also kind of confounding variables, such as Lawrence Berkeley National Labs that contained Berkeley but was not quite Berkeley. So we wanted to know how we could make this decision on this dirty data set. So our first pass was, OK, there were a lot of sensible things we could do. We could take out obvious errors. There were sometimes errors related to HTML scraping. Sometimes there was extra punctuation in these strings. So we did that, but that only went so far. So we had to dig a little bit deeper, so we came up with a set of rules. We said that, OK, well, if one string is contained in another string, they likely refer to the same institution, such as University of California at Berkeley and Computer Science Division, University of California at Berkeley. But very quickly, this broke down. We got something like this. Department of Physics, Stanford, University of California. University of California is actually contained in this string. So these hand-tuned rules actually sometimes have some issues with it, and we could set out and try to design an NLP system to address such a problem. But the challenge is, if we just got this data set and it was in front of us, as data scientists, how can we get to work right away, instead of having to hand-tune some potentially unreliable rules? So we thought this would be a great example of using crowdsourcing. We call the crowd, and that's where you guys come in to actually help us make this decision. Who publishes more, Berkeley or Stanford? And you guys will identify which affiliation strings actually point to Stanford and which point to Berkeley. So that's at a high level what we're going to do in this demo today. And before we get started, I want to just talk a little bit about SampleClean and what you guys will actually see. So there are two issues with actually getting the crowd involved in such a process, such as data cleaning. One, there's an issue of scale. Before lunch, we can't give you guys tens of thousands of publications and have you guys churn through all the affiliation strings. That's just not practical. So, and the second issue is the crowd's going to work a lot slower than our automated components. So how do we cope with these problems? And Dan is going to talk about this in much more detail in the research section of this talk. But the basic idea is that we use sampling to cope with scale. We're going to show you guys only a sample of publications. And we also use asynchrony. So as results stream in, we will update our counts for Berkeley and Stanford. So now it's your turn. And before we dive right in, I'm going to lay some of the ground rules, and I'll tell you guys how to get started. And I'll put up a little bit running tally so we can see who actually wins. So the basic idea is you're going to see a screen something along the lines of this. You're asked the question, are these the same institution? And you'll get two strings, something like University of California, Statistics Department, Mathematics Department, University of California. And if two strings refer to the same institution, so that means they could be different departments, we consider them the same. So there are going to be some tough ones, such as Lawrence Berkeley National Labs and University of California at Berkeley. We consider these different because the LBNL is, while sometimes the researchers from LBNL are affiliated with Berkeley, that's not always the case. So we're going to say no in this case. Now, there are going to be also some easy cases where it's Stanford and Berkeley. So we're going to say, in this case, no. And finally, there are also these weird ones like ICSI, which we also consider distinct from Berkeley. So let's get started. So if you guys visit sampleclean.org/demo, you can actually see these counts update in real time. And we're going to put up an online dashboard that actually shows, as you guys are doing these tasks, our results updating. So Berkeley's in blue, Stanford's in red. And so far, we've done a little bit of data cleaning. And we'll show the progress in real time. And we'll run this for about a few minutes. And then we'll jump right into the research part of the talk. So if you guys have any questions, Juan is over there. He'll help answer. We can also answer some questions. He'll be our kind of roving TA. So, yeah. The cats, that's your reward for doing 5 tasks. No.
Our friends over at thecatapi.com, if anyone's interested.
No, it's something that's very critical to the machine learning algorithms that are going behind the system. So as you guys can see, we've gotten the first set of results in, and we've seen these counts change. And we're hoping that progressive results will really help data scientists not have to wait until the entire crowd finishes until they can actually start their analysis. So if you wanted to make a decision, you can actually make it on early results.
You guys need to start cleaning better because Stanford's winning.
So we'll give it a few more minutes, and then we'll kind of jump back to the talk. So maybe. So if there are multiple institutions, if they overlap in any way, then we consider them the same institution. So as you can see, the changes have actually started leveling off, and this is kind of a general pattern. Like, there are diminishing returns to data cleaning. And so I think that this might be a good kind of turning point to switch over back to the talk.
Stanford won.
This is actually a hard decision. It's actually kind of a hard, it's a hard thing, and the counts are actually very close, so we thought it would be a great example of why you need data cleaning. If you were to look at the raw data, it's very hard to make this decision. So.
All right, cool. So if I could have everybody put their amazing cats away, I will promise to be at least half as interesting as the cats. So in the demo that you guys just went through, we had you clean up this really dirty Microsoft academic search data set. And I wanted to point out that, yeah, this is one really dirty data set, but the problem of dirty data in general is a problem that everybody has. And I'm sure many of you in the audience know this better than even I do. But if you go anywhere on the internet these days, you're going to run into dirty data. This is from Amazon.com. There's duplicates in the data, 2 identical iPhones. We found this cool used car site that somebody posted a truck for $420,000, which is a bit of a markup over the market price of $48,000. And if you go on any page on Wikipedia that has, like a table of data, you'll find missing values, you'll find stale values, you'll find out-of-date data values. The problem with this is that we can't just sort of wave our magic wand and make data cleaning go away, right? Data cleaning itself is really hard for a number of reasons. First is that it's time-consuming. Some of you might have seen this New York Times article that came out a few months ago in August, I believe. They interviewed a number of data scientists and found that people spend, up to 80% of their time doing what they call janitor work, which basically comes down to transforming and cleaning your data. Data cleaning is also costly. When you have really big data sets with lots of error in them, by the time you've fixed all of the issues, you've spent lots of resources, both in terms of human computation if you're using people, and also in terms of computing resources as well. And finally, data cleaning is domain specific. If you have errors in your data, they're likely going to be specific to the data that you have. We saw this in the demo just a moment ago. we were asking you to tell us whether these two strings referred to the same institution, but we had strings that said like Department of Mathematics and Department of Chemistry, right? And just a naive algorithm doing some sort of string featurization might think that these things look pretty different. But in actuality, the semantics of our data told us that they were the same. So fixing errors in your data can be pretty hard due to sort of domain semantics. In fact, this problem's so hard that people often turn to crowdsourcing to do this for you, right? There are platforms like Amazon's Mechanical Turk, where you can hire literally thousands of workers and pay them basically to do exactly what you guys did in here, a couple of cents every time they tell you whether two institutions are the same or not. The upshot is that because data cleaning is hard, the way it often works in systems where real-world analysts are trying to use dirty data comes out something like this. You get data incoming into your system. It's really dirty, so you have to run your big data cleaning pipeline. Unfortunately, as I mentioned a moment ago, data cleaning is really hard and slow and expensive, and so this takes a while. But eventually, your data is clean, and you can pull it into your favorite analytics stack. We favor Badass for fairly obvious reasons. And then you can go ahead and do your analytics. But the SampleClean folks, myself included, took a look at this workflow and said, you know, this is pretty bad, right? And data analysts are actually sitting there waiting around being unproductive while their data is cleaning. What if we could instead bring the data cleaning inside the analytics stack so that data becomes actionable as soon as it enters the system and progressively gets better over time? This sounds like a nice pipe dream, but there are some obvious questions. For example, you know, how could this possibly scale? I just told you that data cleaning was slow and expensive, right? As a crowd, you guys maybe cleaned a couple hundred tuples, but our data sets might be in the terabytes. Especially when we involve people, people operate on completely different timescales than machines, and so you're really worried about the slowdown that might come out of this. So as Sanjay alluded to before we started the demo, there's two insights that we can leverage to make this system functional. The first is that asynchrony hides latency. When you guys did the demo, there were two things going on at once. There was a data cleaning process, which was all of you in the crowd telling us which institutions were the same. And there was also a query processing task going on at the same time. This interactive dashboard that we were showing you was actually issuing queries against the data as it was cleaned. And the important insight is that those queries didn't have to block until data was cleaned. You just ran the query, and it gave you an approximate answer based on whatever data currently existed. So when new data comes in, you just run a new query, and you get a new result. The second big insight is that sampling can be used to hide the scale of your data. Now, if you've been coming to AmpLab talks before, or are familiar with some of the work that comes out of the lab, you might have heard this pitch before, especially in the context of a system called BlinkDB. BlinkDB does this trade-off. If you process your queries on only a sample of the data, you can trade off the time it takes to run the query, right? Running on a sample is very fast. But you also introduce a little bit of error, so you only get an approximate answer because you were only looking at a sample of the data. So that's the BlinkDB pitch, which has been successful, but there's a fundamental limitation if your data is dirty. If there's error in your data, no matter how big of a sample you look at, you're never going to get past the error in the data when you're looking at your query results. So with SampleClean, we offer a similar trade-off to BlinkDB, except we trade off not only just sampling for query error, but also sampling for data error. So if we clean a sample of the data, we can extrapolate to the full data set. So with a system like SampleClean, the flow of data through the system now looks more something like this. We have dirty data coming in. We immediately take a sample of that data, and then we run asynchronous data cleaning. So the second dirty data is in the system, and users say, I want to clean this data, it begins getting cleaned. And sort of at any point in that process, a user can issue queries against the latest state of the data. This workflow sort of breaks down neatly into the two pieces I was talking about. The first half is sampling, where we take samples of the data, and the second half is asynchrony, where we clean your data in the background. I'm going to talk mostly about the asynchrony part today, because sampling, again, the BlinkDB story covers it, and we actually, with related to the data error, we've published a paper on it not too long ago. So let's look at the high-level architecture of our SampleClean prototype. When you enter the system, you're a user, and you have some dirty data. Or for this purposes, we're going to assume you've already sampled that data. And the first thing you do in our system is you declare cleaning operations. You say, these are the things that are wrong with my data, and here's how I want to fix them, in a declarative programming model. And the system has this abstraction of data cleaning pipelines that let you specify these things and then run them on your data. Those pipelines call out to a data cleaning library that we've built. It's extensible, so we're hoping that sort of the same story as MLlib. If there are experts in data cleaning who write algorithms and want to contribute them, we'd love to have them in our data cleaning library. we've built the library with a number of primitives, including algorithms from MLlib, communication with crowd workers via some crowd APIs, and some hybrid techniques, most specifically active learning, that lets you sort of get training data with your humans and then train algorithms with that data. And so the data cleaning library takes the dirty sample, takes the user's instructions from the pipelines, and outputs a clean sample over time. And then we have an approximate query processing module that lets users actually issue queries and get results. So I'd like to walk through each of these components one at a time. I'm going to start with approximate query processing. Again, as I mentioned, I won't spend very much time on this because we already have a couple of publications on this. There's the BlinkDB paper, and then we have a paper on SampleClean that shows how we extend those results to deal with data errors as well as sampling error. But the basic high-level idea is that here we're trading off query error against time. And I should point out that this works largely most effectively for aggregate queries. So we're looking at things like counts and averages and sums. But there's work that indicates you can extend this to UDFs using bootstrap sampling, and we might go in that direction as well. So that's our approximate query processing. The next interesting piece here is the data cleaning library, and this is, in a sense, the heart of the system. The idea is we'd like to allow crowds and machines to work together in order to build these pipelines that will clean your data in the background as we go. So we built an extensible library. There are tools in there that are automated, there are tools in there that are human-powered, and there are tools that are hybrid. And again, the human stuff, we have a sort of a generic crowd server that lets you talk to multiple crowds, Amazon's Mechanical Turk being one, or you can have your own private crowd. And the automated libraries leverage MLlib whenever possible. I want to point out one more time that crowds are really, really slow. Every time we talk about humans, things are going to slow to a crawl. And so one of the things we're interested in with this data cleaning library is how can we let you clean your data using humans and machines and have that all happen sort of in one cohesive flow. And the key to this is active learning. So the idea behind active learning is that what we'd like to do is have crowds look at only a subset of our data, train models on that subset, and extrapolate using those models to the rest of the data. That's great. So you could do this with sort of traditional machine learning, right? You block out your training set, you get your labels, you featureize the data, and then you train an algorithm. What active learning lets us do is show as few points to the crowd as possible while training high-quality models as fast as possible. And the way it does this is by picking sort of informative points to show to our models. So there's a couple examples up here on the slide. Example number one is a not informative point to show to the crowd. Right? We have two strings, Stanford Department of IEOR and UC Berkeley stats. These strings, they look very different, and they refer to different institutions. So the second you have a halfway decent model, it's going to know to tell these apart very easily. And giving it this example as a training example won't help very much. In contrast, the example at the bottom is a little trickier. Right? These are two different strings. Both contain Department of Mathematics. They both contain university. But actually, one refers to Stanford and one refers to Berkeley. So giving an example like this to the model could be quite useful, because the strings do look similar, and yet the entities are different. So we have this data cleaning library that uses automated components, human components, and this hybrid active learning strategy. And tying them all together are these asynchronous pipelines that users can specify their data cleaning operations to, and then run those on the data. So a key idea here, right, is when you have dirty data, in general, more than one thing is wrong with your data, right? It's not just there was the issue, and once you fix the issue, your data is perfectly beautiful. There's all sorts of things wrong. So we let users group data cleaning operations into pipelines, which is basically just a set of operations. And we have a simple programming model that supports that. So you can instantiate a new pipeline, and you pass into the pipeline the data cleaning operators you'd like to perform on your data. In this case, we've got like some string cleanup, which is actually what we did before we showed you the demo. And then normalization is sort of a general name for what you guys were doing with institutions. We have a categorical variable, which is institution, and we wanted to resolve all the messy versions of each category. Once you've declared your pipeline, you can simply execute it. And you execute on a sample of the data. And once you call this exec, the data sort of begins immediately being cleaned in the background. At any time in the future, you can register queries with that pipeline. You can say, run this query on the data for me. And you'll get results immediately, but the second argument to this function is a callback function. Because this data cleaning is happening asynchronously, we need a way to let the user know when the data has changed significantly enough that their results are going to be different. So you pass in a callback, and we tell you at that callback, hey, your data's changed. Here's the new answer to your query. So stepping back, here's our SampleClean architecture in sum. Users do two things. They declare data cleaning operations and build pipelines out of them. And then they issue queries against the data as it gets cleaned. So that's what we've done so far. We have this prototype implementation, but there's still a lot of challenges ahead. Many of these are pretty open research problems. In particular, dealing with human workers still has a long way to go, right? Getting them to perform in terms of giving you accurate answers and fast answers is tricky, and there's techniques we can use to get better at that. These pipelines we talked about, they're declarative, right? Users specify the data cleaning operations they want to run, and we have to figure out an optimal execution plan to actually physically clean the data. And so there's an optimization problem here that's interesting future research. And finally, the programming model deserves some attention as well, right? We want to make sure that users who are cleaning their data and running analytics have an intuitive interface that they actually find useful. And finally, of course, this is the AMP lab, and we wouldn't feel good about ourselves if we weren't releasing our code to you guys to play around with. So we're targeting a release of the system that's going to be integrated with the rest of the badass stack sometime in the next year. So in summary, because data cleaning is slow, costly, and domain-specific, we've built a system, SampleClean, that brings data cleaning into the badass stack so that you can run analytics non-blocking the second you get your data. There's two key ideas that accomplish this. SampleClean uses asynchrony, data cleaning in the background, to hide the latency, and also uses sampling to hide the scale of your big data. And it's worth pointing out as just a final thought that there aren't a ton of systems coming out of the lab here that actually combine algorithms, machines, and people all into one system. And this SampleClean system is really quintessentially AMP, and we're actually quite proud of that. So thanks very much, and we'll take some questions. So the question is about, can we segment our crowd into multiple groups? Like if you know that some crowd workers are higher quality, can you send tasks to them first, or can you prioritize them? Yeah, or give them more voting power. So the crowdsourcing literature has a lot of work devoted to this. There's statistical techniques you can use as you observe workers' responses over time to sort of learn who are the good ones and who are the bad ones, and preferentially weight their responses. In our demo, we didn't do any of that. We just got 3 votes and took the maximum. So, we don't have APIs for that kind of low-level control over crowds. What we've built is a standalone server that communicates with a bunch of crowds, and the API looks more like, I have a bunch of tasks I want to run, and I have a crowd I want to run it on, and here's some settings about the number of votes I want to get. We do actually let you choose to use this expectation maximization algorithm, which lets you preferentially weight good users. So it's a bit of both. Oh, sorry, repeating the question. The question was, what exactly do we mean by dirty data? Do we mean missing data? Do we mean incorrect data? What exactly are we talking about here? In general, we mean both of those things. They have different implications, however, for the statistics of your data set, right? So when we're trying to give you error bars on your query answers, missing data will have a different effect than incorrect data.
Yeah, so I think that's a great question. I think this is part of the reason that we've tried to build. Okay, so I think, okay, sorry about that. So the question was, how do you know your data is dirty to begin with? And this is a great question, and this is something that we're really working on. This is why we want to formalize this programming model. This is why we built a prototype dashboard. And this is really one of the reasons why we've kind of thought about this from the perspective of BlinkDB, that there's some interactive process where you're exploring your data, and then you realize things are dirty, and then you decide you want to clean it. So, but that's a great question. It is definitely future work for us.
All right, so it's lunchtime. After we thank the speakers, it's all right, so it's lunchtime in a second, but before you go, it's my third and final reminder to move your USB key to your computer if you haven't done so already. If you don't know what I mean, come find me after, but hopefully everyone has heard this spiel before. Also, if you're a TA, please come find me because I want to talk to you guys real quick. Anyway, just to let everybody else know what's going on, though, it's lunch until 2 o'clock. At 2 o'clock, we'll all meet here real quick, We will give a high-level overview of what's going to happen for the exercises, and then we're going to split up into 3 rooms. Most people are going to be here, but there's 2 other rooms so that the people, especially in the back, have tables and are able to actually do work. There's 2 other rooms. People will show you where to go, but we'll spend a couple hours on exercises. All right, have fun at lunch.
Oh, thanks. Thank you.